Hopefully everybody can hear me. Before I get started, I just wanted to take a moment to thank Jim and Anna and Andrea and the whole rest of the ElixirConf team for putting on such a great show. And also thank you to all of you. It really means a lot to me to have people take the time to be here and listen. So thank you to everyone. My name's Matt Trudel. I'm an Elixir hacker here in Toronto. And the title of my talk today is Bandit on the Loose, Networking in Elixir Demystified. My main goal with this talk is to take the wraps off a pair of libraries that I've been writing over the past year or so, named Thousand Island and Bandit. They're ground-up reimaginings of the Ranch and the Cowboy projects, respectively. Both of these libraries represent pretty significant advancements in the state-of-the-art of networking in Elixir, both from an ergonomic perspective, but also from a performance perspective. I've had an absolute blast of a time working on them, and I'm so excited to finally show them off in public to everyone today. Another primary goal of this talk is described in its subtitle, and that is to demystify lower level networking in Elixir. You know, all too often, I think people consider networking code and server implementations as kind of being unapproachable and intimidating, but really nothing can be further from the truth. If anyone caught Desmond's talk yesterday, he mentioned he had a great statement there where he said all problems are solvable. And networking code really is no different. I'd actually go so far as to say that lower level networking code showcases really some of the best things that Beam and the OTP have to offer. The patterns and the features that set the Beam apart really shine when you get down to these lower levels, and I'm super jazzed to take all of you on a tour through all of it today. I'll be introducing Thousand Island and Bandit kind of in due course during the tour. But in the meantime, I've organized this talk along the lines that most people think about networking, and that's kind of as a stack. So specifically, we'll be looking at the stack that holds up Phoenix, and it looks kind of like this. From the lowest to the highest level, which is how we're going to explore things today, we start with TCP/IP, we then have sockets, HTTP as a protocol, Plug as a library, and finally Phoenix sitting on top of it. There's an awful lot to cover here today, so we're going to jump right in, starting with TCP, and more specifically, starting with IP. So IP, really, its most fundamental job is to provide every host on the network with an IP address. And that's kind of definitional to what it means to be on the internet in the first place, is to be able to have an IP yourself and be able to reach any other host on the network via their IP. The important thing to realize here, though, is that all IP does is deliver packets to hosts. It doesn't know anything about applications. It doesn't know anything about processes or users. All it does is deliver packets from one machine to another. The job of actually identifying individual applications and users belongs to higher level protocols that get encapsulated inside IP. The most common one of those that we'll be talking about today is TCP. So TCP provides application level addressability on top of IP. And what that really means is that you can take an IP address and a port number and be able to address a specific application running on, on a remote machine. Once you make a connection to that remote machine, the connection comes in the form of a pair of reliable streams. These are basically one-way streams, one running in each direction, and they're binary streams that essentially data goes in one end and comes out the other. The directions are totally independent. They can be shut down independently. They can be used simultaneously, and they're most commonly accessed via an API that's colloquially known as the Berkeley Sockets API. This is it's shipped as part of just about every operating system today. And that's really about as far as we're going to talk about TCP/IP today. This was probably the shortest of the 5 sections and frankly, probably review for most people, but it's really foundational, kind of just the same. So moving from here up to sockets, this is where we actually start talking between remote processes. Be forewarned, this is going to be the longest of the 5 sections. It's also probably the most interesting for most people, as this is, in my experience, where people's understanding is kind of the blurriest about how this stuff works. So let's jump in. So as I just mentioned, the TCP/IP stack is accessed via the Berkeley Sockets API, and the core of that API really consists of about a half dozen or so functions that look like this. Clients use the connect function to connect to an IP port pair. Servers use the bind and the listen functions to bind to a named port, to bind to a specific port number. Servers then call the accept function in a loop, and every time they call accept, they service a request from an individual specific client. Once that connection is accepted for a client, a TCP session gets created between the client and the server. The two peers can then use the send and receive functions to be able to send data back and forth to each other. And at any time, either peer can close the connection. In Elixir, we access this using the GenTCP functions on the GenTCP module within Erlang. And the functions on that module map just about one-to-one onto the standard Berkeley calls that we just saw. SSLs accessed in a very similar manner using just about identical functions. The core abstraction of secure sockets is really just a secure socket. It's the same abstraction of a socket as TCP. And for the most part, you can usually just replace GenTCP with SSL in addition to a few extra steps for handshaking and stuff. And in code, that looks like this. This is a very simple GenTCP server that we'll just walk through it line by line. The first thing it does is listen on port 4000 and then returns a listen socket back to us. We use that listen socket, we call it in a loop around this accept and handle function, and we use that listen socket to go in and listen for a specific client connection. This call will block until a client connects to the server. When a client does connect, we have returned to us the socket that represents the connection to that particular client. We then send the string hello world to that client, close the connection, and call accept and handle to go and process the next request from the next client. On the client side, it's a little bit simpler. We use the gentcp.connect function to connect to a named IP port pair, localhost and 4000 in this case. We then wait to receive data from the server. In this case, we receive the string hello world. Once we've received that string, we close the connection and we're on our way. So graphically, this stack looks like this, at least at this point. At the lowest level, we have the operating system. The operating system exposes Berkeley sockets via the socket.h header in libc. The Erlang runtime then via, it's a port driver implementation in Erlang that layers on top of Berkeley sockets and provides a GenTCP interface up into Erlang user land for us to call to. And this is really all you actually need to implement the server. But working this low level is super tedious. Doing this performantly is not trivial at all. You want to make sure that a long-running client doesn't block you from accepting requests from other clients. And so this is usually abstracted into a pattern called a socket server. Now, a socket server's main goal is what I just described. It provides an abstraction on top of raw sockets, and it usually sits underneath a higher level application, such as a web server. It listens for connections over whichever type of socket it's configured for, and it hands those individual connections when they're received up to that protocol layer for further processing. It also handles sort of secondary bookkeeping concerns, such as certificate negotiation for SSL, shutting the server down cleanly, and just other bookkeeping functions. And of course, it does all of this efficiently and scalably. The go-to socket server these days in the Ruby in the Beam world, is Ranch. Ranch is written by the same person, Loic, that wrote Cowboy. I've written a new one called Thousand Island, written entirely in Elixir, and inspired pretty heavily by Ranch, but with a number of improvements. Just for starters, one of the main improvements is that it's no slower. Performance is basically equal to Ranch. This is kind of unsurprising considering that they fundamentally do the same thing in very similar ways. And it is about as fast as you can really get this kind of a model to be both performant and scalable. It's about half the size from a line count perspective as Ranch. We still have feature parity with Ranch. We're about half the size from a line count perspective. Comprehensively documented, lots of examples, very well tested, supports all of the standard socket types you would ever need, fully supports all configuration options that the Erlang layer underneath it supports. We just proxied the options right through. Fully wired for telemetry, including socket level tracing. So this is really cool. You can use telemetry to jack into a particular socket connection and actually see the bytes coming and going on the wire. Tremendous for debugging. But probably most importantly is it has a very simple, powerful, and really expressive handler behavior for higher level applications. And that's what we're going to look at right now. So this is an implementation of the datetime protocol, which is a really simple one. When a client connects, the server sends it the current time in some unspecified format, and then closes the connection. So we implement this by implementing the Thousand Island.handler behavior, and we implement the handle connection callback on that behavior. This function is called by Thousand Island whenever a connection is received from a client, and it passes the socket for that connection into us. We then go and format the time as a string, and we use Thousand Island.socket.send to be able to send that string to the socket. And then we return close to Thousand Island, which tells Thousand Island to close that connection. A somewhat more refined example is the echo protocol. This protocol specifies that the server should wait for data to be received from the client. It should echo that data verbatim back to the client and then continue doing that until the client closes the connection. So once again, we implement the Thousand Island.handler behavior. This time we implement the handle data callback on the behavior, which is called by Thousand Island whenever data is received from a client. It passes the data in as the first argument. We then take that data, turn it around, pass it back to the client using the socket.send function, and we call continue back to Thousand Island, which tells Thousand Island to keep the connection open and continue waiting to see if there's more data coming. These two functions are really the core of the handler process, and that process is implemented. There's one process per connection, so per client connection. And the Thousand Island.handler module that we just saw is really just a gen server inside that process. The cool thing about this is that your process can then go and do all the other gen server things it normally can. In addition to handle connection, handle data, and the other half dozen or so functions that are defined, callbacks that are defined in the behavior, you can handle calls, handle casts, run things on your process, do whatever you'd like to do. Receives from the client are asynchronous by default using the handle data function we just saw. But you're also free to write traditional blocking network code using the send and receive calls anywhere you want. You can do this on Thousand Island calls, on gen server handle calls, any place you'd like to in that process. And if all of this is too restrictive, there's also a start link based escape hatch if you want to sort of just plug into Thousand Island at an even lower level. These individual processes inside Thousand Island are hosted inside a process tree that's rooted in the Thousand Island start link call that your application uses to start the Thousand Island server. And that process tree is entirely self-contained. There's no backing application. It's entirely supported for an individual host to run any number of Thousand Island instances, each on different servers, each on different ports, rather. And internally, those process trees are this multi-level thing that we've designed to minimize contention at all sort of steps of the connection lifecycle so that it remains performant under any type of load. And it's really kind of a textbook example of how powerful OTP design patterns can be. To be able to do this as simply and expressively as we have is really kind of a testament to how awesome OTP is. The project README file at the URL at the bottom of the slide has tons of examples and tons of description of how this works. So that's Thousand Island. To summarize the kind of current state of the project itself is stable, suitable for general use, feature parity. We have essentially a complete feature parity with Ranch. We're currently on the 0.5 release series. This is likely to be the last before an eventual 1.0. We have big ideas for the future post 1.0, largely around multi-node setups and managing clusters of Thousand Island nodes transparently. But the foundation that you've seen here is and should remain solid. So this is what the stack looks like so far. On the left-hand side, we've got the Gen TCP interface we saw before with Ranch layered on top and Ranch exposing the Ranch protocol up to higher level applications. On the right-hand side, we have Thousand Island layered on top of Gen TCP, exposing the Thousand Island.handler interface up to higher level applications. So we're going to move up the stack now and talk a little bit about HTTP. So HTTP is really just plain text over sockets, at least HTTP 1.1 is. And it looks like this. And many of you have probably seen this or maybe even done it over Telnet before when you're debugging a server. The client makes a request. In this case, it makes a request to get the resource thing/12. It describes some headers, passes some headers that describe some parameters of the request, possibly a request body. The server then determines what to send back, sends back, in this case, a 200 OK response code, some headers that describe the response, and the body of the response. Now, the simplest, I'll note that in SSL, it's the exact same structure here, simply run over SSL sockets instead of TCP. The vast majority of the HTTP protocol is unchanged in both cases. So this is kind of what a simple HTTP server would look like in Thousand Island. Once again, we use the Thousand Island.handler behavior. We implement the handle data function, except this time we ignore the data that's passed in because we're actually going to just send back a static 200 response code with a static body of hello world, and then we close the connection. This is a valid server. If you load this up in Chrome, you will see hello world. Chrome will not complain, but it's obviously not super useful. When you think about what goes into making a useful server, though, it's not really that much more complicated than that. Fundamentally, we're parsing a request body from a client, possibly reading the body in, figuring out what to send back to them, and then sending that back to the client conformantly. And a few implementation, this is, I mean, what the core of any implementation does. The go-to implementation of this in the Beam world today is Cowboy. Again, written by Loic, the same person who wrote Bandit. It is a complete implementation of HTTP 1.1, as we just saw, as well as HTTP 2 and WebSockets. I've written Bandit, which is a new pure-Elixir HTTP server written specifically to host plug applications. And I'm going to tell you a little bit about that right now. So Bandit is written 100% in Elixir, and it is plug native. Its entire job is to serve plugs. That's all it does. And as a consequence, we also support really robust HTTP and HTTP2 conformance, written from the ground up to be correct, to be performant, and to be really easy to understand. Again, part of my goal with these projects is to kind of demystify networking code for people. So clarity and readability is really kind of important here. And this simplicity also drives some pretty incredible performance numbers that we'll see in just a little bit. So turning back to how you actually make an HTTP server do useful things, you need to return content. And that content is going to be the content from your application, right? The question is how to actually hand off from an HTTP server to an application server. And in the Elixir world, that's the job of the plug library. So we're going to move up the stack now to plug. So plug looks something like this. It's an abstraction of HTTP requests and response pairs. And if anybody's seen Rack in the Ruby world, it's a very similar pattern. The core of it is really the call function, as you see here. Now, this is called by plug, by your web server implementing plug, whenever a request comes in from a client. The first argument is a plug.con structure that describes the parameters of that request. Your application then uses functions on the plug.con module to describe the response it likes to send back. In this case, it's returning a 200 response code with the body hello world. So they're pretty simple, but they're actually really, really powerful. And they're powerful largely because the plug library comes with a bunch of useful parts built in. It comes with plugs to create pipelines, to compose plugs together. You have routes to be able to route based on various patterns, we'll see in a moment, to do a bunch of other useful things that you need to do in the common course of running an HTTP server as well. And this is actually enough for an awful lot of applications. In fact, the original project that spurred on the development of Bandit in the first place runs on these basic building blocks to this day. And I'm actually just going to take a quick sort of sidebar to highlight that, as I think it describes some useful tools that you might not be aware of. So Bandit was originally written to support HAP, which is a HomeKit accessory protocol library I've written that allows essentially nerves devices to be able to be controlled from an iOS device and just participate in the HomeKit ecosystem. And the HAP protocol runs over HTTP, but with a little bit of a twist that they have this kind of one-off custom encryption that runs on bare TCP. I started trying to do this in Ranch, and I kind of gave up pretty quickly. And that's what actually spurred the development of Bandit and Thousand Islands so that I could get lower level and do these things myself. But the HTTP that runs on top of this is actually really simple. And in the case of HAP, it runs entirely on the plug.router module. Plug.router provides a really simple DSL that allows you to kind of match HTTP requests against patterns, so posting to pairings or getting accessories in these cases, and be able to craft responses in a really lightweight manner. Reformed Rubyists might recognize this as being very similar to Sinatra, and it is. So if you ever find yourself thinking that Phoenix is a bit too heavy for a particular job, I would suggest looking at plug.router, as it might really fit your needs quite well. So turning back to plugs, after that little sidebar, let's look at how web servers actually call into plugs. So in the Cowboy world, this is implemented via the plug.cowboy adapter, which is an adapter written by Jose that adapts from Cowboy's internal handler behavior into the plug pattern. Bandit has a bit of a leg up here because we are plug native. And so in a stack perspective, it looks kind of like this. On the left-hand side, you've got Cowboy sitting on top of Ranch with the plug.cowboy adapter, stuck in there, and then it serves plugs up to your application. On the right-hand side, we've got Bandit that sits directly on top of Thousand Island and serves plugs up to your application natively. So that's about everything we have to say about plugs. We're going to finally turn our attention now to Phoenix. And it shouldn't surprise many people at this point, but Phoenix, at least the HTTP part of it, is just a plug itself. It sits on top of the stacks we just saw. The WebSocket support in Phoenix is a thing apart. I'm going to talk about that in a moment. But this is really about as far as we're going to go in the stack today. Graphically, we're at this point here. We've now layered Phoenix on top of the respective plug APIs on the Cowboy and the Bandit side. And I'm going to take the rest of the talk now that we've kind of described the full stack that sits underneath Phoenix, and talk about why I think Bandit is a really compelling option and a really compelling alternative in that stack compared to Cowboy. So just to review, Bandit is an HTTP server written specifically to serve plug applications. Obviously, it's built on top of 1000 Island with full support for HTTP 1 and HTTP 2. We don't yet support WebSockets, coming to that in a moment. We score 100% on the H2 spec conformance suite. This is a Go application, and it's kind of the gold standard conformance suite for HTTP2 servers. We run this as part of our CI suite, in addition to the usual battery of EX unit tests. And the whole thing is kind of written top to bottom to be, again, really clear and approachable and just unsurprising, idiomatic Elixir the whole way through. One of the things that I want to talk about, focusing in on how Bandit is a plug-first web server, is the fact that there's no impedance mismatches. Every bit of code in the project is there with the sole purpose of getting from web requests to plug calls and back again. And this means that not only is the code clearer, but there's also less of it. At the current time, we're about a third the line count of Cowboy. Now, this isn't an entirely fair comparison because Cowboy does support WebSockets. I suspect by the time we're fully we've reached feature parity with Cowboy, we'll probably be about half their line count, but we're still much, much smaller. And this simplicity kind of gives us some really incredible performance and memory numbers, which I'm going to talk about now. So in a recent benchmark that I've run, Bandit is up to 5 times faster than Cowboy, depending on your level of concurrency and the type of, whether you're serving HTTP 1 or HTTP 2. On the low end, we're 1.5 times faster. On the high end, we're up to 5 times faster. And I want to be clear here that I'm not juicing these numbers at all. This is as good faith of a comparison as I'm capable of doing as a non-professional benchmarker. And in fact, in several cases doing these tests, I actually had to give an advantage to Cowboy because it couldn't complete some of the more highly concurrent tests without crashing. Unless I missed something stupid here, I really do believe that these perf numbers are this good. In both these cases, they're totally out of the box configurations for both Bandit and Cowboy. The process behind these benchmarks is at the URL at the bottom of the slide, if anybody wants to take a review of them. But these performance numbers, I think, really come from how streamlined our approach actually is in building and how we built Bandit. And we're going to take a look at that right now. So HTTP 1 in Bandit uses a single process per connection. This is in contrast with Cowboy that uses 2 processes for every HTTP 1 connection. And there's just about a direct mapping between the handle data calls that we saw earlier when we were looking at the handler behavior and plug.call calls. The code that get from a handle data function to a plug call is very straightforward and linear. There's not really a whole lot of there, which is why I think we're able to be as fast as we are. The HTTP2 side is quite a bit more complicated, and it's more complicated largely because HTTP2 is more complicated. The primary design goal of HTTP2 was to be able to allow a single connection between a client and a server to service multiple HTTP requests simultaneously. And it does this by multiplexing those requests, by breaking them up into small frames, these binary frames, that each correspond to a part of an individual request. The HTTP2 protocol calls these streams. At any given time, the client may be sending headers for one stream and the body of another stream, while the server is returning the body for a completely different stream. And you can kind of see that in this diagram here. This is all quite a bit to handle, and we handle it like this. In Bandit, we have a single process per connection, plus we have a single process for each stream, so for each separate client request within that connection. The connection process implements the Thousand Island handler behavior that we saw earlier, and it kind of faces the client and manages everything to do with the network connection. The stream processes are the ones that actually make the plug calls, because recall that streams correspond exactly to HTTP requests, and they kind of face the plug API. And then the majority of the implementation just involves coordinating those processes against one another. In addition to this, we also support all the other goodies in HTTP2. We do flow control, we do push promises, continuation frames, pings, go-aways, all the goodies in the protocol are there. We use IO data structures everywhere we're able to internally, and that gives us another big boost for speed and memory awareness. So from a status perspective, the HTTP2 implementation in Bandit is complete. It's exhaustively tested. That was the main goal of the 0.3 release stream, which landed last month. We're now turning our attention back to HTTP 1.1. The current implementation kind of dates from the earliest 0.1 days of the project. And we're just more or less going over it and tightening the screws on it, ensuring that it has the same, comprehensive test coverage that the HTTP2 implementation does. And that's the purpose of the 0.4 release stream that we're in right now. At this point, I think the project is suitable for non-production use. We don't support Phoenix. I'm going to talk about that in a moment. But for the places that we are a suitable drop replacement, we are basically a drop-in replacement for Cowboy. In most cases, it's literally a matter of changing the word Bandit to Cowboy in a few places. The startup parameters are the exact same, and Plug obviously is the entire job of Plug is to abstract the server away from you. So for the most part, a drop-in replacement is all you need. Obviously, looking to the future, the biggest thing that we're excited about is Phoenix support. The biggest impediment there is landing WebSocket support. This is going to be coming in the 0.5 release stream of Bandit. I will note that WebSocket support is outside the scope of Plug, and Phoenix actually realizes WebSockets right now by reaching into Cowboy's internal implementation of WebSockets. In addition to this, we also have plans to integrate with Phoenix more broadly in terms of the startup and configuration and just general process hosting within it. Beyond this, also plans to obviously continue driving performance improvements and to improve our story about how to make it easier to migrate from Cowboy over to Bandit, where there are issues with that. Driving a PR campaign to essentially let people know about the project. Getting more users means we fix bugs faster, means we get to a 1.0 faster, and eventually long-term supporting things like HTTP3 and Quick. All of this is kind of table stakes for what the actual long-term goal of this is, and that's to become the de facto networking stack for Elixir and the Veeam. I'd like to one day see Bandit as the default or a default choice for new Phoenix installs. I'd love for this to be the stack of choice that people reach to for all manner of networking in the Veeam, along with Thousand Island, of course. And judging by the responses I've received from dry runs of this talk and just from other evangelism I've done, particularly with Thousand Island, there's a huge amount of excitement that I'm seeing from people being able to start writing low-level networking applications without the intimidation of having to jump into Erlang, which is unfamiliar to a lot of us. So I'm really, really excited to see where this goes. Obviously, that's an ambitious goal, and to get there, it's about collaboration. So the biggest thing in the near future is working with Phoenix to be able to add Bandit support. Depending on the reception from the Phoenix team, I'd love to look at generalizing their WebSocket interface into something similar, basically Plug for WebSockets or something along those lines. Andrea and Eric from the Mint HTTP client project were kind enough to abstract their HTTP2 header compression library out of Mint into a library called HPACs, which I'm now using within Bandit. So thanks for that. Thanks very much for that, you two. And it's great to see code sharing like that between clients and servers. Some other things as well, some improvements to speed up IO lists and ERTs that I have in mind, and some other sort of more minor upstream improvements with mostly to do with Plug. While we're speaking about our friends, I want to be perfectly clear here that I'm not throwing shade at Cowboy and Ranch at all. They are fantastic projects. Loic does tremendous work on them. And they are and continue to be probably the right choice for most people, at least for the near future. Obviously, these are both open projects. It's really fun foundational work. At least personally, this is the type of work that I enjoy most, that I'm best at. I would love to be able to do this kind of stuff all day. Infrastructure code, again, really doesn't deserve the reputation it has as being unapproachable and mysterious. And I think if you jump into these projects, you'll see how approachable this stuff really is. They are grassroots projects. This is stuff that I'm doing entirely after hours. So while resources are thin in that respect, there's also a huge opportunity for any of you to jump in and leave as big of a mark as you'd like on either of the projects. We've got a number of sort of things that are, kind of top of mind right now in terms of places we'd love help. Looking at the HTTP 1.1 implementation and the WebSockets work coming up. Improving our property testing story, white hats to be able to do an audit of the project, to be able to see any holes that we can fix, and really anything else other people have in mind. That brings us to the end of our talk today. Hopefully you come away from this with some new nugget of networking knowledge. Again, I'd really encourage anyone, with even a passing interest in lower level code to take a look at Bandit and Thousand Island, try to understand them, maybe even contribute. Again, a big part of their existence is to demystify this stuff and to get people to be less terrified of networking and infrastructure code. So don't be shy. We do have about a minute or two left in questions. If anybody has any that we don't get to, or that they just don't feel comfortable asking in public, do feel free to reach out. My Twitter, my Slack, and my email are here. I will be on the Toucan. I'll be on Toucan right after this talk. And I guess at this point, we'll open it up for questions. thanks everyone very much for listening. Again, thanks Jim and Anna and the whole ElixirConf team for putting on a great show. And I hope to talk to all of you soon. Thank you.
Thank you. Thank you so much, Matt. It was super interesting, your talk. We have a comment and we have a question. We can quickly go through them. The comment is from Travis Griggs. Okay, and he says that he writes APIs, but not so much web apps. So using Phoenix to do APIs sometimes feel like driving a semi-truck to work. I would love to see some documentation similar to, and he's sending us a link that shows bare bones secure APIs.
I'm not sure. I'm not familiar with the link that with the story that he's passed there, but the answer to that, I think, would probably, the first place I would recommend to look at is the plug.router module that I spoke about. That's the one that I use in the HAP project for the HomeKit stuff, and it's essentially like the simplest possible thing to be able to match on patterns of URLs, and you can even extract, IDs and stuff out of those patterns as part of how you match against them. And then being able to, like, for example, parse JSON and throw JSON back at a client is like literally 3 lines inside one of those DSLs. I might suggest looking at the HAP project for that at /mtrudel/HAP on GitHub. For a couple of examples about how we use the plug.router project, the plug.router module in that project. You can also look at the plug API documentation itself. It's fantastic and talks pretty directly about plug.router and plug pipelines as well.
Thank you so much. We have time for another 2 maybe. So this one is from Ben, and he's asking, can
yes,
one drop this?
I believe you can. I haven't gotten around to doing it yet, mostly because despite all of this work, I've actually written like 20 minutes of Phoenix in my life. Like I'm a very, very low level developer by preference. So I haven't actually had a whole lot of exposure to try to do that. In theory, yes, exclusive of any of the WebSocket stuff and any of the process startup stuff within Phoenix. There's nothing that says that we shouldn't work. We do completely support the entirety of the plug API in Bandit, which in theory is all that that Phoenix knows about with respect to the HTTP stack. So it should work. The longer answer is I'm going to be digging into this pretty extensively as part of the 0.5 work, which I hope they'll start in a month or so, maybe. So we'll definitely have more answers there. But in theory, yes. Other than WebSockets, we should support Phoenix today.